The great thing about this OpenCV course is that you can follow along from any computer without installing any software by using Google Colab in your browser. Ms. Ba, who teaches this course, makes it super simple to follow along if you already know some Python.
Hello everyone, welcome to this OpenCV tutorial series. Here we'll be using Python in Google Colab to create OpenCV projects, understanding the basics of OpenCV. We will understand the color profiles, doing edge detection, image manipulation. These are all simple applications of OpenCV, and then gradually move into the intermediary applications like color detection, writing, drawing, shape detection. We'll also try to do some projects using the knowledge that we have amassed in this particular tutorial to create ball tracking, face recognition, and so on. This tutorial series is designed for people who are beginners, intermediary, and people who just want to enhance their knowledge in the OpenCV field. We are using Colab, which will allow us to create these applications right off of the website on the Google Colab library. We don't need to worry about downloading some dependencies, installing libraries, and making sure things run or not. Having it on Colab makes it very easy plug and play for us. With that, let's get started. Hello, welcome to lesson 1. I'm going to quickly make the screen big, and I will also upscale this thing so the visibility is right good for you. So in the description, you can open up this link and it will take you to this page. And basically the first step we're going to do is simply run this clone. So we're just cloning the repository. We are just downloading all the files that we need for this program. So it makes our lives easy. If you go into this folder, you'll see this OpenCV tutorial folder created for us, and it has some sort of images that we will be using for this particular set. So the first step, the first lesson we want to look into is changing a color profile of an image. So the first thing you want to do is import OpenCV, and that's the mother, father of everything, of all the images. So you want to download OpenCV first, and make sure OpenCV is happy and it takes care of all our images to the best of its extent. Now we also want to display the images, and since we are using Google Colab, it's in order to display it right in the browser, there is a different function, and for that purpose we will import from Google, because Google had created this patch for OpenCV, and you say Google Colab dot patches. So you have patches from Google Colab patches, import CV2 IM show. Then the purpose of this guy, CV2 IM show, is just to take your image and display it on the browser. So as simple as that. Now you have OpenCV and you have OpenCV IM show. Now what do you need? You need the images to work on. So the first thing is to read the image, and I'll say, okay, I have an image and show me how I read the image. So OpenCV has this command called imRead, and this is basically stands for image read. This image read guy can take whatever image you have and just read it in the program in this Python application. What does imRead need from you? It only needs the path of the image file. So where is our image located? Our image is located, this is the color.jpg, this is the image that I am interested in, and it is available inside this images folder of color.jpg. So we will say, okay, I have my image, it is in the images folder, bracket, and the slash, and you put down color.jpg. So that is my image. So imRead just needs for you to guide and let him know where the image is stored. So I'm just saying it's under images, color.jpg. So it's as simple for now. Now let's try to read this image. Let's try to display this image for now. So we can use this imcv2 show command, and we'll do show, and this show only needs you to tell what image you want to show. And in our case, we just want to display this image. So we say, this is the image you want to show us. So once you have this, just go ahead and run this, and it should open up the image for us. You can see it's a very colorful, very vibrant, very displaying image for us right here in the browser. Now, I am interested in what is the dimensions of the image, what are the properties of the image. And for that purpose, let's not display it again. We write, hey, OpenCV, tell me what is the dimension, what is the property of the image. And that is stored under the function, under the variable called shape. So I will run this and it displays this function and this number. And what is this? What does this stand for? So 476 and 640 are nothing but the number of rows and number of columns, or the width and the height of the image. And this number 3 represents the number of channels that are available in the image. Now, since this image is a colorful image, it has 3 channels, which is nothing but the red, green, and blue channel. And that is what defines a colorful image. So this is basically a colorful image. Now, the first thing we will look into, since we are talking about colorful profiles or changing the color of the profile of the image, the first thing we will look into is making an image grayscale. Now, grayscale image, what is this? It's basically a black and white image. Now, let's see how OpenCV can do it for us. So we will call a new image called gray, and we will say, hey, gray image, make this colorful image turn into gray for us. How do you do it? You just go into OpenCV 2, and OpenCV has this amazing function called as CVT color. And this color function is capable of converting the color of any image that you give. So you need to just let the function know what image that you need to provide. In this case, we'll say our colorful image from the previous section, please convert that into gray for us. So we say image, but it also needs to know what kind of color you want. So yes, I know you have given me the image, the colorful image, but what do you want in return from me? So for that purpose, we say, hey, OpenCV, convert it into a color from color to gray. So we say convert color in caps lock and an underscore. And we say, hey, OpenCV, convert it from BGR to gray. So we just say this and it converts it for us. And we say BGR because our original image is in the format of blue, green, red, all the 3 channels separate. And we convert it into a gray image. Coming down, let's display this image for once again. Now, let's see what does the gray has in store for us. And let's run this, and voila! Our colorful image is now turned into a grayscale. Now, you might ask, hey, Misbah, you had a very beautiful, colorful image. Why did you bother converting it into a grayscale image? Why do you even need to do that? Aren't you spoiling the image? Aren't you going to spoil the program? What is the purpose of converting it into a grayscale image? The purpose for that is these 3 channels. So you can see the colorful image had 3 channels. And these 3 channels store information about the red color, green color, and blue color. And that is a lot of information for us. When you're going to be using OpenCV algorithms and computer vision programs, you have to do complex processing, pixel level processing. You're going to be opening each and every bit of the image. And that's too much of information for us. So in order to reduce that, one of the techniques is to reduce the number of channels. So like this colorful image had 3 channels. If you were to display and ask OpenCV, hey OpenCV, give me the number of what is the shape of this gray color image. And if you print this, you can see that the colorful image had 3 channels and the black and white or the grayscale image has no channels. So you can see there is nothing available here because it's only one matrix all by itself. It doesn't have any channels. You have reduced, you have compressed all those 3 channels into one channel, which is defined by a gray color profile. So you have reduced the information, you have reduced the number of pixels, you have made OpenCV happy because now it doesn't need to handle 3 different channels for your images. Just one image, there's just one channel, and that's all it needs to take care of. So you're making OpenCV happy, you're making your computer happy because it doesn't have to load so many bits of information for you. And this makes life easy for you and for the program. So let's go into the basics. Now we have the grayscale image. Let's look into another print, another type, and that is the HSV image. Now you might ask, okay, so we took out all the color profiles. We took out everything we needed from the color images. Now we brought them into a gray image. But what if I was interested in color? I'm a colorful person and I am interested in identifying different colors in my image. And that is my project. But you made it into grayscale. Now how am I going to work on it? Well, to answer it for that is your HSV image. And this HSV image or this HSV channel is capable of holding all the color profiles under one channel. Now, what do I mean by that? To appreciate that fact, remember this. Your colorful image had 3 channels, right? Blue, green, and red. The HSV image will also have 3 channels, but the channel that defines the color is only present in one bit. So I'll explain what that means. But let me say, hey, OpenCV, I'm going to create a new image called HSV. And for that purpose, I want you to convert my original image. And I'm going to use again this convert color profile function. And I'm going to pass OpenCV the colorful image that we had, image. And we're going to let, hey, OpenCV, this original image that I have, convert it into a HSV image. The HSV color BGR to HSV. And if I just print the shape of this HSV dot shape, and let's run this. So you can see HSV also has 3 channels. So what are we doing then? Well, HSV stands for hue, saturation, and variance. And the hue is defining all the color profile in the image, all the colors that are available. Blue, green, red, everything, all the colors of the rainbow are going to be available in this just one channel called each. So if you can control, if you can pinpoint H to give you red color, you can also pinpoint it to give you yellow color, green color, blue color. So this HSV guy, the H channel of this guy can hold all the colors of your image. So previously, this colorful image had 3 channels, and in order for you to define a color yellow, you would need all the 3 channels to define what a yellow color looks like. But a HSV image can only use your H channel to define what color you need. And that makes your life in detecting colors very simple, very easy, and very, very easy for the computer to process. So your complex algorithms that we will look into the future will be very easy to run. You might ask, how does this HSV image look like? Well, you don't want to see it, but I'm going to do it anyways, and you might regret. Let's run this. And you can see that this HSV image looks nothing like the colorful image, nothing like the grayscale image. It has its own legend, and it's running, it has an own property, it has its own way of displaying images. And that is what we are interested in. we are going to look into the H value, the S value, and the V value separately to define the color that we are interested in. So with that, we come to the conclusion of our first chapter, which is changing the color profiles. And these are the color profiles that are going to help us in our later projects. Welcome to lesson number 2. Here we're going to look into what edge detection is all about. So the first step is to go ahead and import OpenCV. So OpenCV can take care of all our manipulations, image manipulations that we're going to do right now. And we have this image, which is right under this directory. If you go under OpenCV tutorial, you have this images folder, and under images folder, you have this image color.jpg. So we'll work with that image today. We will say, hey, OpenCV, I want to read this image and I want to save this in this variable called image. So image is equal to cv2 imRead, and you need to tell OpenCV what is the image file path. So in our case, we saw that it was under the images folder and it's called color.jpg. So that is the file path for us. We just go ahead and write down the image path name, which is under images, bracket, and just specify what is there after the slash, and you say color.jpg. You are now specifying what is the image that you want to read. Once you have this, if you want to just simply display it, you can use cv2 imShow, and that's how you display it. But since we are not able to use, we are using the Colab version, we cannot directly use cv2.imShow, and for that purpose, we will import something called as or from Google. Google has this patch that created in order for us to use the cv2 imShow. We will use Google Colab.patches import cv2 imShow. So we are just importing cv2 imShow, and we will say, hey, cv2 imShow, please display the image for us. We just specify the image, and if we run this, it will display the image for us right here in the browser. We can see our colorful image is right up and running for us. Now, let's go into the edge detection. So we have this image, let's, for now, we'll comment it. Now let's make it into a canny image. We'll say canny image, and this canny image is nothing but the edge detected image. We're going to be using an edge detector called canny edge detector. Are going to be using this function from OpenCV, which says, hey OpenCV, cv2, please do the canny edge detection on my image. So OpenCV has this function called canny. You just need to specify what is the image. Okay, I have the image. The canny edge detection also requires you to specify the size of the filter that you're going to be using. So the filter size in our case will specify, hey, let's go to be 150 by 200. It doesn't matter what filter you're using. You can always test it out and see what kind of a result are you getting. So there's no hard and fast rule behind the 150 and 200, which I mentioned here. You can always test it out and see. And now we can simply display this. But before we display, there is an issue. Canny image does not run by its own. It needs to run on a grayscale image. Like the grayscale image that we learned in the previous lesson, where we were converting the grayscale using the color BGR to gray, we need to convert our image into a grayscale image before we do anything. So let's copy this. Let's copy this line from here and come back to our canny edge detection. Now we know what is the purpose, what is one of the uses of grayscale image. We save this here and we convert our image into a gray image, and we specify the gray image to canny because canny is only able to work on grayscale image. It only assumes that the image has one channel, and for that purpose we need to make sure you're only providing one channel grayscale images. And let's see how this image runs out to be. So now you can see the whole image is gone and it's only specifying the edge profiles of the image. Isn't that amazing? And that is what the canny edge detection is capable of. There are a few more adjectives, there are a few more things that we can do with this. We have the canny image, and it's able to detect all the linings, able to detect everything, all the edges that are available in the image. But say we were not interested in everything. We were only interested in the highlighting features of the image, because right now it's very difficult to understand what this object is even about. So we can use some filtering methods. And for that purpose, let's import NumPy. Import NumPy as NP. And NumPy is our brother to OpenCV, who is able to do some matrix manipulations for us, which is also very much similar to what OpenCV does. In fact, NP can also be another format of OpenCV because it also works with matrices. But OpenCV has already made things very easy for us. So we are not going to ditch it. We're going to use it simply and run our application with the help of OpenCV. Now, you have NP. The next step we're going to look into and understand erosion and dilation. We'll say erosion and dilation right here. So let's first do erosion of our image. Now we can do erosion by saying, hey, erode my image. Which image? The canny image. And erode it so that you can remove some of the filters that I'm not interested in. Erode the image by using OpenCV's erode function. And this erode function is capable of taking your image, which is the canny image. You have the canny underscore image, but it also needs for you to specify a window size, because this window is going to move over your image, and wherever that window matches or falls into the property of erode, it will eradicate it. Oh, you know what? I just found my mistake. So I missed the E over there. And we are also needed to specify the window size, which is also called as the kernel. The kernel equal to NP, since we are going to be using NumPy to create our matrix, and kernel is a small window, a small matrix. So, and it's going to be a matrix of ones, and we'll give it a size of maybe 5 by 5, and we'll say NP is of unsigned integer of bit size 8. That's basically specifying what our image is going to be looking like. And this 5 by 5 is nothing but a tuple, so it should be under brackets, and you have your kernel defined right here. We use the kernel into our erosion format. We say kernel, and it can also you can move the window over the image multiple times. Right now, we're just interested in one time, so we'll say iterations equal to 1. So erosion, going back to the function, there are a few things happening. So the erosion function is able to take the image that you're interested in. It also needs the kernel, and it also needs the number of iterations you are going to specify it. So let's display this image as well. CV2 IM show erode image. So let's do erode image and now run this. So we are going to run this image, and for some reason we're getting an error, and the error for here, it says that as a substitution consider CV2 underscore IM show, and we as a user of OpenCV on a desktop, we use the .im show function. Let's convert that into the underscore, and let's run this, and you have a new image which has nothing. It basically eroded everything. So let's reduce the kernel size and say 2 by 2, and let's see what kind of a result we will get. So it has some information. You can see some dots available. So of course it's taking out most of the information. And now you might ask, why do we even need to do this? Because it's taking out all the information that is available in our image. Let's make it by one and see if it can display some more information. Yes, it's displaying a little bit of more information, but if you compare it with the previous image, there is not much of a difference. And it makes us think or doubt ourselves about why do we even use erosion. Well, erosion is used in order to reduce the noise level in the images, and it also comes and it's very much useful when we can pair it with dilation. So let's look into what dilation is. Dilation is nothing but the opposite of erosion. So let's go into dilation. Let's maybe comment this out for now. And we say this is erosion and this is going to be dilation. So dilation also needs the kernel. Yes, so we can put maybe the kernel on the edge side. So we'll put the kernel right before everything. So it's the main guy because it uses both erosion and dilation. So we'll have kernel in both. Now we said, hey, dilated image, use OpenCV's dilate function. Dilate and use your canny image. Let me move this out of the way. So you're using OpenCV's dilate function, and it also requires the kernel that we created, the kernel, and we also use the iterations equal to 1. So what we did is we are using the dilate function, which is very similar to what the erosion function is. Now we are using it again on the canny image. We are making the kernel, we're making use of the same kernel, and we are using iterations of 1 by 1. Let's see what we can get if we have the kernel size of 5 by 5. And let's display this for us. I am show OpenCV dilate image. Let's run this, and we can see this is the canny edge detection image, and this is the dilated image. What is happening here? You can see that the edges, or all the edges that were visible here, now they have been emphasized. They are made more, they are increased, or you can say dilated. They become very big now. Now, if we were to use erosion after dilation, let me remove this kernel. We don't need the kernel, or we can keep it for your purpose. That's fine. And let's do erosion after dilation. So we have your dilated image, and we'll use the dilated image instead of the canny image, and then display our eroded image. So let's run this. So you have the original canny image again. Then you have going down, you have your dilated image, and now you have your eroded image. So you can see there's a difference between the canny edge image and the eroded image. So there's a little bit of doubts here. So if we increase, let's see what else we can do to make it more simpler for us to understand. So we have the canny image and the eroded image. We are basically converting, we are basically making or displaying them one after the other. What if we do it horizontally stacked? So we have this np.headStack. We use display. This is the image that is going to be displayed, and NumPy has this function called hstack, and hstack is going to take 3 values, and our values are the canny image, we have the dilated image, and we have the eroded image. So we use all these display images, and we say cv2im show display this image instead of displaying the eroded image, instead of displaying the dilated image, instead of displaying the canny image altogether. We will display all of them under one horizontally stacked. We just run this, and we can see all the 3 images right here in front of us. So you can easily compare what is happening to the original canny image. The edge detected image has made it dilated, so it becomes big, and now you're eroding some parts of it so that it can become more and more visible, and you're just trying to basically erode some of the more abundant information available here. So this is more about erosion and dilation, and the number one use of canny edge detection with use of erosion and dilation is in the process of making lane detection applications. So you have a road, you have a picture of a road, or you have a video of a road, and you are interested in understanding where the lanes are available. And for that purpose, you want to use the line detection, the edge detection, and then provide dilation and erosion if there are any kind of noise you want to remove. So the erosion and dilation is nothing but to use or work with noise for our purpose, and that helps us in making the image more visible, so that you're not focusing on the unnecessary information, but focusing on what we need. Maybe it could be the edges, maybe it could be a certain region within the image. So you can specify your filter size and then focus on the area that you are interested in. Hello everyone, how's it going? Today we're looking into image manipulation. Now, image manipulation has a variety of things that you can do. If you just go into OpenCV and type in image manipulation, you'll open up this OpenCV's program, and let's look at image manipulation of OpenCV. If you just go into image processing and OpenCV, you will see that it consists of color spaces, changing color spaces, doing some sort of geometric transformation, thresholding, smoothing of images, which is nothing but all these noise and blurring images, morphological operations, which include of erosion, dilation, and opening, closing, etc. Erosion dilation is something, if you recall in the previous video, if not, if you haven't seen them, I'll put the link in the description. You can look into this erosion and dilation, and this is basically removing the noise or adding or emphasizing those pixel values. Similarly, you have image gradients, you have canny edge detection, you also have image pyramids. So these are all different types of image manipulations that you can do, and we will look into some of these important ones which we need to know for sure into subsequent chapters. But right now, let's look into one particular aspect, which is denoising, or which is also called as removing the noise, removing the issues that you come across in these images. Now, in order to run this, once you open the Colab link, you can go ahead and run this code, which is in the very top, and it's basically the GitHub clone, and you're just cloning the repository that we need here. So it'll take a few seconds and it'll clone the repository. And if you open up this folder, which is the directory folder, you'll have this OpenCV tutorial, and it'll have this images. Under images, today we have this new image called the lion image, lion.jpg image. And the reason we have this lion.jpg image is because I wanted to get a very grainy and a very noisy image, and animals, because of the hair, amount of hair present on them, it seems to be very noisy on a camera. And especially lion with all the big hair available on it becomes very noisy. We'll look into the code and see how this image really looks like. So we're going into lesson number 3, image manipulation, and let's read this image for us. So we are importing OpenCV, we are importing CV2 underscore IM show, and we are also importing NumPy. Now let's look into displaying this image first. The image equal to CV2.im read, and we want to read the image under the OpenCV folder, because our image is under the OpenCV folder, OpenCV lion.jpg. Let me maximize this a little bit so it's easier for you to read. In fact, I can close this as well. Now we know it's under the OpenCV images. I think we are already under the OpenCV folder. We just need to be under the images folder, because we already changed the directory right on the beginning. If you see, we have changed the directory to OpenCV tutorial. So the cursor is somewhere in here. We just want to go under the images folder. So for that purpose, I'm telling the images, that image which I'm opening, it's under the images folder. The images, then you have the lion.jpg. So this image should be read into this folder, into this variable called image. And once we have this image, we will now display it. We will say CV2 underscore IM show image. And if we just run this, it should display the lion image for us. You can see it is this big image, and it has so many hair on it, and it seems very noisy if you look at it from a camera perspective, from an image perspective. Of course, those are the definitions of the hair of the lion. I don't know what it's actually called, but you can see the number of grains, the number of noisiness available here. Now, consider that, okay, this is something noisy picture, and you're not interested in looking at all this images, looking at all these hair profiles of the lion. How would you remove this thing? How would you remove or blend all these hair profiles into one? And for that purpose, we have something called as fast and mean denoising color. And this is a part of OpenCV's denoising profiling. So if I go under OpenCV image denoising, you can see that it's taking a grainy image. And this is from the website, or this is from the OpenCV's website. So it is a very grainy image. You can see the amount of noisiness that's available. And once you apply the denoising filter on it, it removes the noise to a large extent. And how it's doing it is because it's averaging the pixel. It is taking the mean of the pixel in that area, and whatever is available, which is more important, it then denoises it and just takes out what is important for us. And this is what the denoising takes care of for us. We'll come here and we'll apply the same denoising filter on our image. And the denoising filter looks like something like this. Fast and means denoising colored. And it's the reason we are putting colored is because this is a colored image. Similarly, OpenCV has something for grayscale, where you can do more about binary images where it's only black and white, and they have their own functions which act in a separate way. In this case, we're using the colored profile, and we need to provide the image that we want to do. In our case, it is image. And these are all the filters that are available. So because this is, it's kind of a filter, it's kind of a window that goes over all across the image, and it displays all these images for us. So there is a filter which basically goes through all these images, and then this is the size of those filters. These are the threshold values. So all these values are something. Right now, at this point, you don't need to remember what this is about, but when you're using this program, this particular function in your real-time code or project, then just play around these values until you get the result that you want. Now, there is no hard and fast rule in knowing what is correct and what is wrong, because every size of every image is different. The project that you're working is different. The type of images that you're using is different. The size of the images are different as well. So all these values will differ from the different images that you're using. In my case, for this particular image that I'm playing with today, this particular values worked out, and but it could be different for different. And we'll see how this thing works a little bit as well. Now, coming down here, let's display this image. So you have the original image, which is the image, and the destination image, which is DST. Now, let's use a NumPy to create a horizontal stack of this. So we'll create a horizontal stack, which we will be displaying, and we'll call it as a display. And horizontal stack is basically adding both these two images, destination and image, and making it look like one image. So the NumPy has a function called hstack, and it can take two variables or two or many variables of similar size, similar matrix size. So we can say, okay, hey, I want to add the image and I want to add the destination together. And both of them, please combine and give it to me under this variable called display. So we have display, come down here, and we will use OpenCV's underscore _IMShow display. And it will display this for us. Let's comment this thing so we're not displaying it two times, because already we are displaying the image and the destination here for our case. Now let's come here, let's play this, and it should run both the commands, and it should give us the output right here. Oops, jumped up. Okay, so you can see both the images are available here, and this is the original image, which has all this grainy profile of the lion. In this case, you can see that all the grains, all the hair are blended and they are joined, and you can only see the gradient color out of it, and all the hair profile, which was basically defining the features of the lion here, are gone, and it's only emphasizing the gradient profile of this. So it's basically considering all these hair profile as noise and removing them and giving it out to us. So it looks like a more of a cartoonish display of an image, and converting or cartoonizing the image. But it's kind of a representation of those images here for us. So now coming down here, let's play with these values a little bit. So you have 20. Let's see what happens if we do it as 5. And let's run this again, and we'll see what kind of an output we get here. And since we reduced the size of the window, you can see that the grains are now much more visible. There is, of course, a little bit of blurriness available here. You can see this portion here, and this portion is different. Whereas the long hair available here are also available here, because the size of the filter reduced, and it's only now removing small amount of noises. So because the texture you see here on the nose, it has small noises, and those noises are being blurred out. However, the big hair profiles that are visible, that are still visible in this final image. And that's because you have reduced the amount of the filter. Similarly, if we increase to this thing, say for example, we were to do 50. Let's see what kind of an image we may get. Let's see even if we can even recognize whether it's an image of a lion or not. And you can see that it's fully blurred out. You can hardly identify any kind of features in this image, and it looks like more of a painting without much definition of the original character. And you can see this thing more looks like something from 3D, something from a cartoonish drawing. And all these features, all these things has been blurred out, and it's only showing the gradient of it. And that's how it affects all these filters, all these values affect the value. And similarly, you can play with all the other values and see what kind of an image you get out. And this is basically helpful when you're doing some sort of image or foreground extraction or background removal, where you want to specifically segment or specifically emphasize on the objects and remove all the types of noise available in the image. And, that's how it's very helpful. So with that, we come to the conclusion on image noise removal. Hello everyone, welcome to lesson number 4. Here we're going to try how we can draw shapes and write text on images. So OpenCV has their own drawing functions and own writing functions, and we'll see how we can use that to our own images. So the first thing you want to do here is import our OpenCV. So OpenCV can take care of all our OpenCV, our own manipulation functions. Once you have image, we maximize it a little bit. So once you have OpenCV, the next thing you're going to be using in this project would be NumPy. Import NumPy as NP. And I'll go into why we're using NumPy in a little bit. We're also going to be using Google Colab's CV2IM show so that we can use and display the images right here in the browser for us. So we are importing from Google Colab patches, import CV2 underscore IM show. So we have all these 3 libraries right here. Now, normally we go into the directory and try to open one of the existing images. But in this case, we will create an image from the scratch, from the basics. So the first thing we will do is we will use NumPy to create a matrix for ourselves. So we'll call a matrix called IMG. Okay, so this is our matrix with IMG. And now, what is NumPy going to create a matrix for us? So a NumPy has this function called zeros. And this zeros function is capable of creating a matrix of just zeros. So the zeros function is going to return a matrix which is just filled with zeros. And with OpenCV language, 0 is nothing but black color. So now, since we are going to be using a colorful matrix, we will create a 3-channel matrix. I'll go into that right now. So let's first define the size of the matrix. We'll say, okay, let's call it a 5 by 12 and 5 by 12 matrix. So it has about 512 rows and 512 columns. So that's the definition of our matrix. And this matrix is also going to have 3 channels. These 3 channels are representing the red, green, and blue color of a colorful image. But in this case, we know we are initializing it with zeros. So all those three channels will basically be 0 at the moment. But we want that, and the reason we want that is later on we can fill in the colors that we want. So we have our matrix, which is 5 by 12, 5 by 12, and 3. And we are also going to say, okay, NumPy, this matrix is going to have a property where the numbers are going to be unsigned integer of byte size 8. Now, what does that mean? Unsigned integer of byte size 8 means the range of the values inside the image or inside the matrix are going to be anywhere between 0 to 255. That is the meaning of unsigned integer. So basically, you're just defining a matrix and you're telling that this matrix is, yes, it is 0 in color, but later on in the future, when you're going to be adding new colors, it's going to add in this range only, and it can take a range of values only between this 0 to 256. And that's because colors are represented in a 256 range, which starting from 0 goes to 255. So you're just defining that this is unsigned integer. Okay, now let's display this. Let's see how this image looks like. We've been talking about zeros, we're talking about black in color, but let's actually see how this function works. Oh, you know what? It should be IM show. So we have our image. Let's display this. We have run this, and you can see it's nothing but a black color image, not even white, black image altogether. So we have taken care of the image, and now our image is present. So let's try to do some manipulations on it, like some drawing functions. So OpenCV has a couple of drawing functions. It can draw a circle for us. It can draw a line for us, a rectangle. It can put text. So there are a couple of things that OpenCV allows us to do. Now let's see how we can go about doing that. OpenCV has a function called circle. So we'll use this circle function. We'll call it as draw a circle. Let's see how we can do that. OpenCV has this function called circle, CV2 circle, and this function can define, you can see it takes the image name, the center of the circle, the radius of the circle, the color, the thickness, the type of the line, shift, and then it gives out the result in your image function. So this is what the circle function does. Now let's define. The circle function needs the image, which is the img. It also needs the center of the coordinate of the image. So we will say, okay, the center of our image in this case is going to be at maybe 100 and 100. So x and y are both 100. Okay, good. We have this. Then the next step you want to put down is the radius. We have the radius, let's say maybe 50. Okay, we have a radius of 50. Next thing you want to do is the color. So you want the color. Now color is represented by 3 variables, which represents the BGR value. So in this case, let's make it a green color circle. We'll call it as, because since it's represented as BGR, where B is for blue, G is for green, R is for red, we will call it as 0. And since we want green color, we'll put green as 255, which is the highest value, and the red is again 0. Once you have the color defined, the next thing you want to do is the thickness of the line. So thickness is also something you can define, and we will call in our case a thickness of size 10. Okay, so let's see how this function works for us, and then immediately after that we are going to display our image. And let's run this, and you can see that now we have a circle. It's a circle which is green in color, and it has a thickness of about size 10. So that's about drawing the circle. You can always play with these values. These are nothing too crazy about. You can make it a size thickness of 5, and you can see the thickness as radius from the circle. So that's pretty much about this drawing a circle. Once you have drawn the circle, let's see how we can draw a rectangle. So again, OpenCV has a function called rectangle, CV2 rectangle. And this function also takes something similar. It takes the image, it takes the points of the rectangle, and it takes the color, the thickness, of course, the line time and the shift, and we can then draw the rectangle. Now, point 1 and point 2, it says that it draws the rectangle between the two opposite points. So point 1 is on the top left corner of the rectangle. Point 2 is on the bottom right corner of the rectangle. Coming back here, we will see CV2 rectangle. Yes, you want to draw the rectangle on the image IMG, and you want to define the point 1. In our case, the point 1 is going to be, should we draw at 100 by 100? No, but that'll be intersecting with the circle. So let's bring it a little bit away from the circle. We'll call it as 200 by 200. Okay, so it's a little bit further than the circle, and we are going to say that it's going to end at maybe 400 by 500. This is just random. You can choose whatever you want to draw. The point here is just to understand how we can draw these parameters, these rectangles and geometrical shapes on the images. So we have point 2 defined. Now we want to define the color. Let's make this a red color rectangle. So we'll call it as 0 for blue, 0 for green, and 255 for red. Now, let's minimize this a little bit so we can see what's going on the other part of the screen. So we have 255. We also want to specify the thickness of the rectangle. The thickness of the rectangle is going to be 5, for example. Let's run this and see what we can do on the image. And now you can see that there is a rectangle coming up. And this rectangle has about the same thickness as we had for the circle because both of them are 5. So once we have the circle, let's see what happens if we put the same coordinate as the circle. 100 by 100. Same, it's 0.1. And let's see what we get. And you can see a rectangle that is intersecting the circle. And then it's also bigger in size because the 0.2 has not shifted. Let's bring it back to where we are so it doesn't messes you up when you are trying this code on your own. Okay, so we have the rectangle, we have the circle. What are we missing? The line function. Let's draw a line. So OpenCV has this function called, let me put down the comments here so we know what we're doing here. Draw a rectangle, draw a line. Okay, so CV2 has a function called line. Now line can also draw something on the image, and you know a line can be defined between point 1 and point 2. So as long as you know where the points are, you can draw a line. So you are going to be using the image, the point 1, the point 2, the color, the thickness. By now you might get the pattern. So it first takes the image, it takes the parameters of the coordinate of the geometrical shape, and the color and the thickness. The line type and shift is something that we're not looking into, but you can have a dashed line, you can have a broken line, a dotted line, two different types of lines. By default, it'll take a solid line. Come down to CV2 line. So it takes the image and it takes the point 1, and we'll call point 1 as some random value, 160 by 160. Okay, now what is point 2? Point 2, let's put it as a random value of 359, 29. So you have point 1 and point 2, and this time we will give it a color of blue color. So we'll say 255 for blue, 0 for green, 0 for red. So you have the blue color. And we'll give it a thickness of, again, maybe 3. And let's see how we can run this. So we run the play button, and there seems to be an error because we missed the comma between the thickness and the color. So we specified that, and now we can see there is a line drawn right here between point 1 and point 2. So we have the line drawn, we have the rectangle, we have the circle. Coming down to the last point is how to write a text on the image. And we can draw a text, or we can put down a text on an image by using CV2 put text. So it has a CV2 dot put text function, and this function can put down the text that we want to put down. So this also takes the information where it's going to be putting. It's going to be putting on the image. It's going to take the text you want to be putting down, the origin of the text, so the initial coordinate of the text, the type of font you're using, the size of the font, the color of the font, the thickness of the font, and then it draws the text for us. And this text right here is going to be a string. It's going to take a string value and then display it on the image for us. So let's come down to CV2 put text, and we will say, okay, the image img is going to be using to display the text, and the text is going to be OpenCV. And the next step is going to define the origin of the text. And let's say we want to be putting it at 280 by 150. So we have defined the origin of the text. Now we're going to be defining the font face. Now OpenCV has some default fonts that we can use. But at the same time, if you want to use your own font, yes, OpenCV does allow us to use some external fonts. So you can see that it's giving me an option of putting down font underscore Hershey, complex, complex small, duplex, plain. So it has a couple of options. So let's go with what we have here. And we can put down, okay, font Hershey complex, you're ready for us. And the next thing you want to put down is the scale. Now the scale is the size of the font. And we will put down, just for the safety, we'll say 2, because we don't know how big this text is going to be. We have 2, and then the next thing is the color. Now we have already used blue, green, and red. You can see the blue is for the line, the green is for the circle, and the red is for the rectangle. Let's use something different now. Well, we can put down blue as 0. We can have green. We can also have red. I wonder what kind of a color this might give out. Now, the thickness, let's say the thickness is 2. And we can now display this and see how we can, what kind of an output we can get. So you can see that it is generating this text OpenCV. It's starting from the origin that we have specified, but it's going beyond the size of the image. That's because OpenCV does not know, especially the font function does not know where the image is ending. So it keeps continuing printing the text on the image, and if the text is beyond, it simply truncates it, but it does not raise any errors. So the only solution for that is you reduce your image, you reduce your text. So you can either make it a smaller text by making a size of 1. Scale, you made the font size is 1, so it's within the scale. Or you can also use or move your origin. So instead of 280, you can say, okay, we'll put it at the same point where the line is. So we'll say 160 by 160. Oops. 160, and let's close the bracket right here, and we'll put the font scale back to 2 size. Now let's see. So you can see that's now generating the OpenCV. It's of course on top of the line, original line, but it is at least within the image. per se. I guess that does the job for us. In the last, here we are displaying the image for us. So that's the simple function. These are simple functions that can be used, but again, they help us in displaying the data on the images for us. We'll see in the future projects how we're going to be using these functions in our real-time projects. Hello everyone, welcome to part 2, which is intermediate exercises of this OpenCV tutorial series. And we are going to look into lesson number 1, which is color detection. The first thing you want to do is come on to the top of the earliest thing, and come here where it says the cloning the repository and also changing the directory. Let's run this function by itself, and we are only interested in this just because we do need this OpenCV tutorial folder, and it has certain images, and we're going to be using one of these images here for our project. So let's come down here and let's look into the intermediate exercises, and we are under color detection. The first thing you want to do is import all the libraries that we need, and we need import CV2. We also need NumPy as NP. Let me maximize this a little bit so it's easy to read. So import NumPy as NP. We are also going to be importing the Google Colab library for our display. We'll say from google.colab.patches import cv2 underscore imshow. Let me show you what I've done here. So from Google Colab patches, we are importing cv2 underscore imshow. Now we have all these images. We have everything in our folder. If you go back to this directory and under the OpenCV tutorial folder, under the images, you have certain images, and we are going to be using this image called shapes.png. So coming back here, we will say, okay, OpenCV, you know what? I have this image called shapes.png, and I want you to read it. For OpenCV to read this image, we use OpenCV cv2.imread. So OpenCV will tell me, okay, I'm going to use imread to read, but give me the file name. What's the file name? Okay, the file name is going to be shapes.png. But this shapes.png is inside the folder called images. So I will also need to provide the folder path, which is images with a slash. So images slash shapes.png is where the image is available for us. Okay, so that will read the image and it will save the image under the image folder variable. Now let's display this image by using cv2 underscore imshow image. And we just display this image here for us. So we're just reading and displaying the image. Okay, good. Let's run this, and we can see that it is displaying this set of image. It's a big image and which has all the shapes and different colors present in here. Okay, good. Now coming back to the code. So we have the image right now and we are just displaying it. Now say if I was only interested in particular colors. So I have this blue color here. Let's say that I'm only interested in this blue color for now. Okay, so we come here. The easiest way to select blue color is to first convert it into a HSV image instead of a BGR image. Currently, image is a BGR image. It is represented in blue, green, and red channels. Okay. Now we want to convert this image into a HSV image. So we have, okay, coming here, let's come down here. Let's convert this into an HSV image and we'll call it HSV image equal to cv2 convert color. We used this function in, I believe it was lesson number 2. It was right here in the lesson number 1, I believe. Yes. It's changing the color profiles. We used it here for our convert color. BGR to gray, BGR to HSV. If you haven't watched that part, go back to the page where it displays the HSV image. We have given a description of what HSV images are and how do they look like. Now, coming back to the color detection aspect, coming here, we are just using the convert color function to convert our BGR image to a HSV image. And this convert color function requires us to tell what's the original image. The original image is the image variable right here, and we specify the image. After that, we do need to provide what kind of a conversion we're doing. Now, since we're going to be using BGR to HSV, we're just going to say convert color BGR to gray. So we have BGR to HSV, I'm sorry, BGR to HSV. So this function right here, HSV, is going to be converting a BGR image to a HSV image. Now we have the HSV image. Do you want to see the HSV image? If you have watched the previous video, you don't want to do it, but just for the sake of understanding, let's run this. There seems to be a function error. Yes, because we used the underscore. We did not use the underscore, instead we used the dot version. So you can now see that this HSV image is different. It's different to what's available here. This original image has different colors for the different shapes, but here it's almost the same, but it's not the same. Mind you on that. It's a little bit different. Yes, it is in yellow in color, but they have different color profiles, different ranges. And we'll see how we can utilize that factor. Okay, let's remove this. Let's just play this. So we have our color image here. Okay, now what is the next step? The purpose of HSV is because you are converting a BGR, a 3-channel image, into a HSV image where hue, saturation, and variance, hue represents the color profiles. So you can now control the value of hue to display what color you want. So I will say, okay, I have this image. It has different colors and I'm only interested in this blue color. So I can isolate this blue color in the HSV range by saying, okay, my lower blue color, so you need to provide a range of your blue color values. And I'm going to say, okay, my lower blue color, it's under the array. It's going to be an array, and this blue color array is going to have a value of, say, 65, 0, and 0. And I'm going to supply another upper range. Now stay with me on this and I'll explain you what's happening here. And I'm specifying another array, and this array is going to have a value upper bound of 110, 255, 255. So I'm having two upper array. So I have a lower bound and an upper bound. And I use this lower and upper bound to take out or extract just the blue color. Basically what I'm saying here is, okay, I have an image and I'm only interested in the blue color, which is between these two values, lower blue and upper blue. And this lower blue is specified by the hue value between 65 and 110. So my blue color is between 65 and 110, and the rest, the saturation and the variance, is maybe between 0 to 255. I don't care. Right now, I'm only interested in my hue value, which specifies the color, and my color, which is the blue color, is between 65 to 110. And this is what OpenCV will look for. Anywhere where blue color or the hue value is between 65 and 110, it will extract that and ignore the rest. Basically, the value of this color can go anywhere from 0 to 255, 0 to 180, but we are only interested in 65 to 110. Okay, so we have defined the boundaries of our blue color. Now we are going to be using a range function to create a mask. Okay, I am creating a new mask. Now this mask is going to have the value only of the blue color. So OpenCV has this function called inRange. InRange, and this range can take these lower and upper bound range and return the pixels that lie between these ranges, this range. So I say CV2 inRange, and you want to find the range between in the HSV image using the lower bound and the upper bound. So you can see the source image, the lower bound, and the upper bound. Coming back, we've supplied the image, which is the HSV. We are now supplying the lower bound, which is lower blue, and we are also supplying the upper bound, which is the upper blue. And it will create the mask for us. Let's generate this, and we can see how the mask looks like. It'll be a black and white image, which will only consist of blue color. So you can see that this is the original image right from here in the bottom, but the upper image only is specifying the triangle which represented the blue color original. So it's now creating that mask is created where it's only representing the triangle. Now, so let's not display the IM show original image, so we don't get confused. We can see the image now only is creating a mask around the blue color rectangle. Okay, so good. Now the next step is to use this mask to extract the original blue color from the previous image. So we can use a bitwise operation on this. We can say, hey, result equal to CV2 bitwise. Oh, did I move out of it? Okay. Now I hope it's visible now. So we have bitwise and wherever your mask has an image, wherever your mask is white in color, like this case, wherever the mask is white color, it should return the original color of the image, and wherever it is black, it should just ignore that. That's what the bitwise AND is going to do. Wherever white color is present, it will give out the original color, and wherever it's black, it will ignore that area. So we'll say, okay, you're going to be doing bitwise AND on my image, and you're also going to return the image in my same image folder, and we are going to use a mask which is given by our variable here mask. So this is my function, and we have defined the result image. Now let's display this result image. Okay, so we are displaying this result image now. Let's run this. And let's minimize this a little bit so we can see. So you can see the original mask looks like this, and the final image looks like this, where it has extracted the original part of the image. It has the blue color. Similarly, if you were interested in the different types of colors, you need to specify the different lower and upper range values. So like we did lower blue here, instead of blue, we can say lower hue and upper hue, because we are actually converting, or we are actually using or playing with the hue values. So we'll say upper hue and lower hue. So let's run this back again to make sure our code is fine. We did not break anything. Yes, everything seems to be working fine. And we also don't need to display the mask anymore, since we know how the mask looks like. Basically a black and white image, and you can see that this image is only representing the blue color rectangle. Similarly, our original image had different other colors, like it had the red color, the yellow color, and we'll see how we can extract the different colors. So this lower and upper bound range defined the blue color triangle. Now, similarly, there are different other color profiles, which can represent different other colors that you might be interested in. So similarly, like we have blue, we have the red color, and you can use the red color by using our lower hue, and our lower hue is equal to again with the np.array, and this array is going to have a range of values between 0 to 20. So because this red color is basically 0 by 0, it's in the original spectrum of, it's in the initial spectrum of the hue value. Similarly, we are also specifying upper hue equal to np.array, and this function goes from 0 to 20. Hue is between 0 to 20, and our saturation and variance, we don't care. It can be anywhere between 0 to 55. Once we have this, let's comment this so it doesn't affect our original part. So we have the blue, and now we're looking into the red color. So let's run this, and you can see now that it's only showing the red color circle. So it's extracting, it's only isolating the red color from the original image. Similarly, there are different other profiles. So we had the red color. Now we can also look into green colors. Now green color also has its own lower and upper hue, which is given by np.array, and this function of green color goes from 46 to 91. Now you might ask, how am I getting these values? How do I know that red color is between 0 to 20? Well, how is blue color between 65 to 110? Similarly, how is the upper range of green color between 46 to 91? This is more with trial and error. And again, OpenCV also has a function called track bar. Now I'll show you what it looks like. CV2 track bar. And this track bar, it's something which cannot run on a Colab, but you can run it on a standalone desktop application. So this track bar basically creates this kind of a range track bar, and you can change the values of your color, the red, the green, and the blue, and you can see what kind of an output you're getting. And that output, then you can take that and then represent it in your own code. So you know what the upper and the lower bound limits are. Using this track bar, you can always play with it. It's something which is not too complicated to work with. We will see it in the later future projects if we ever get to use it. But if in case you're interested in identifying what kind of upper and lower bounds are, you can always use a track bar to run with it. So looking into green color is between 91, and we are again not interested in the saturation and variance values. We have, let's comment the red color now, and let's run this just for the green color. So you can now see its green color is being displayed very nicely. Now, say if I were to display all the three colors, or maybe red color and green color together, you know the red color starts from 0 and ends at 20, and the green color, on the other hand, starts from 46 and goes till 91. So if I were to say, okay, instead of 46, let's put 0, it should give us both the red and the green color, and maybe some other colors also. Yes, you can see that it can give out the red color, the green, and also the colors between both of them. So you're getting this color also. Let's change this back again to where we were. So we have 46 to 91. Now let's come back and now try to discuss or identify where the yellow color is. Now again, lower blue, lower hue, which is given by an NP array, and this array, this is a NumPy array, and you're defining this NumPy array between 21, 0 for saturation, 0 for variance, and you also have an upper hue and NP array, which has 21 to 45 and 255 and 255. So you can see it's ending up at 45 and then starting at 46 for green color. That's the reason you had both when you try to represent between 0 to 91. So you were getting yellow color as well. Okay, let's comment this and let's run this. And this yellow color is now being extracted or isolated. So you can see Again, if I were to change instead of the 21, if I were to put down 0, it would give us the value of all the three colors, which is the green, the red, yellow, and the green. Now, why is the green missing? Because the upper bound is 45, whereas the green color is starting at 46. So if we were to say, okay, instead of 0 to 45, let's say 0 to 91. And if we were to display this, you can see that it's also giving all the three colors. What if we needed the blue color as well? So again, you can play this value. You can see that the blue color starts at 65 and ends at 110. So if we were to change the upper bound limit to 110, and if you just run this, it should include all the four colors that we wanted. So any color that you're playing with, any color that you're interested in your own images will lie between that range, 0 to 180. So identify whatever color you are interested in and then work accordingly. Okay, let's convert this back again to what we wanted. So we needed the yellow color, and the yellow color is between 21 and 45. So if we just needed the yellow color, let's run this, and you can see that it's only giving us the yellow color. Hello everyone, welcome to this face detection intermediate lesson number 2 under the OpenCV tutorial series. In this tutorial, we're going to see how we can do face detection. And the first thing you want to do is come here where it says table of contents, open part 1, and just before part 1, there is this cloning of repository. This is basically just copying all the files that we need for this project. So we just click on the play and it will download all the files that we need. So if you come down to the directory folder, you can see there is this folder called OpenCV tutorial created for us, and under that there is a file section. So this file section has this har cascade file. If I maximize this a little bit, you can see that it's showing har cascade frontal face default XML. This is basically a cascade classifier that we are going to use in order to do our face detection. Coming back to the table of contents, going to part 2 intermediate series, lesson number 2. Now under lesson number 2, here we're going to code our simple face detection application. It's a simple 4 or 5 line code, very easy to follow. So just stay along with me. Now, the first thing you want to do is import OpenCV. So OpenCV can do all the image manipulation for us. I'm going to maximize this a little bit and remove this so that it's easy for you to see. So you have OpenCV. The next thing you want to do is import cv2_imshow from Google so that we can display our images right here in the pod. In this browser, you have Google Colab.patches import cv2_imshow. So you have underscore, then you have all the libraries that we need. The next thing you want to do is you want the library for cascade classifier, and that's cascade classifier is going to help us in do our face detection. So let's initialize that. And face cascade is a variable that's going to hold the cascade classifier for us. We'll call it as cv2.cascade. Okay, face cascade. Now you are a classifier, so OpenCV has this function called cascade classifier, and you just need to specify OpenCV. Hey OpenCV, you got the cascade classifier for us, but I also need to tell you where my cascade classifier is located. So we saw that it was under this file section, under the har cascade frontal face. Now this is a very big name, so you can see it's called har cascade frontal face with a bunch of underscores in between. Very difficult for me to remember, so I will just go ahead and say rename file, and I'll press my Control-C to copy the file name, and I'll close this. Now I do need to specify, okay, I got cascade classifier frontal face here. However, we knew that was not just the har by itself, it was inside this folder called files. So I do need to provide the file path name as well, which is files. So you have specified that, okay, the cascade classifier is inside the files section, files, not just file. The files section, and under this har cascade default.xml. So you can do a lot of mistakes here, so just pay attention. So you have files, and then you're specifying this thing. One last thing is you want to specify this as a string. because cascade classifier is expecting this as a string. You want to specify under quotation marks, and that's done with the face cascade classifier. Okay, so that's done with the cascade classifier, and trust me, I think that's the most complex part. Everything else moving forward is very easy. Now, the next step is to read one of the images that we have. Now, under this directory here, under the images folder, there is a couple of images, and this image with the person.jpg is basically a human face, and that's the face that we are going to use to test our face detection today. So we'll call it as image. Okay, image. Now, OpenCV, you have this function called IamRead. Please read the image for me. And the image is inside this images folder, and it's called person.jpg. Going back, showing you images, person.jpg. Just specifying that, okay, it's an images.person.jpg file. And once you have specified the image, let's simply display the image. So we know everything is working out perfectly so far. So let's run this, and it's able to display a person's image right here in the browser for us. Now, coming back here, the first step you want to do is convert this colorful image into a grayscale image, because this cascade classifier is designed only and only to run on grayscale images. So you have to convert that into a grayscale image. And how you do grayscale image conversion? Going back to our table of contents, you have changing image color profiles. If you click on that, this section where we learned the conversion of color, this color BGR to gray, this is what we are going to use today in order to convert our BGR image to a grayscale image. So we'll use that same thing. We covered that in the previous lecture. Going back to face detection, let's use our convert color function. So we'll call it as a grayscale image, gray image, and we will use OpenCV's convert color function to help us convert our colorful image to a grayscale image. So you want to specify the image that you are using. You also need to specify the type of conversion you're doing. So since you're doing BGR to gray, you are going to let OpenCV know that it is a color conversion, and it's converting from BGR to gray. So this right here is what we are going to use. And now gray is going to be nothing but a grayscale image. So if I change this IMG, and instead of that we display this gray, it should be a grayscale image for us. So you can see now, yes, it's a grayscale image displaying for us. So very simple. Now this grayscale image is going to be sent to this face cascade classifier. And this guy has been waiting for us to do our face detection. So we'll say, okay, guy, no more waiting. You're ready to do our face detection. So this face detection is going to be run through this face cascade. And this face cascade is now, since it's a cascade classifier, it has its own functions. It has its own built-in functions. You see, the moment I put the dot, it's giving me a couple of options. Convert, detect multiscale, 2, 3, empty. So these are all built-in functions that the face cascade classifier can perform for us. In our case, we are simply going to be using this detect multiscale, and this multiscale is nothing but a detection function which can do image detection for us. So let me go back, close this back again, I'll show you a few things. So the moment you go into that function, this function is going to take the size of the image, or sorry, the image file name, whatever image you want, the scale factor, basically you're trying to tell how big your image is compared to the original training images, the number of neighbors that it can have, a couple of other flags, minimum size, maximum size, which are not so much of concern, but the image, the scale factor, and the minimum neighbors are what we are very much interested in. Go back here. Now you are specifying the image, which is the grayscale image. Then now you're specifying the scale factor. So the hard cascade classifier was trained on a couple of images, a lot of group of images in the past, but those images were of certain size, certain color, certain shape. So those training images were of a different property, and it's very different to what we are using right now. So you're just specifying that, okay, my new image could be of a scale factor of 1.3. Well, it could be anything else. This is just a random number that I chose, and it seems to be working. But if you notice that this number is not working for your own images, just change that a little bit and play around. You'll get the right results. Next thing is you're specifying the number of neighbors. In our case, we don't have any other faces in this image. It's only one face here, but we're specifying, okay, this could have 5 because we're going to be using the same code to do some group detection as well. So it seems to be 5 is working out even for a single image, but we'll see. So we have the faces. Now we use the face cascade classifier to detect all the faces that are available in the grayscale image. And this faces has information about all the faces. So this function is a very important function. This variable has information about all the faces, and let's draw those faces. Now we are going to be using another function, another system that we learned in the past. And this lesson, where we saw lesson number 4 under the basics folder section, drawing shapes and text. So if you come here, we learned how to draw a rectangle, a line, even putting a text. So we'll use one of these functions to do our face detection. Coming back to the directory, table of contents, coming down to the face detection aspect, let's come down here. Now we will use these faces to draw the information about where the face is. So this faces has nothing but the coordinates. So if I print this, print faces, let's comment this, it will have information about the coordinates of where the face is. But these coordinates are nothing but the pixel values of where the bounding box of the face is. So let's come back here. Now we don't need to print this. We will now use these coordinates to draw our bounding rectangle. So we'll say, okay, for X, Y, W each. So this information in faces. So what is that I'm doing here? So this X, Y, W hatch is nothing but the coordinates that are available inside the faces. So the 208 and 73 are nothing but the X and Y location of the top left corner of the rectangle. And this 161 is nothing but the width and the height of the rectangle, of the bounding box which houses the face. So coming back here, we'll say, hey, CV2, you have this rectangle function, which we saw in the previous lecture. And this rectangle function is able to take the image, the point 1 and the point 2, which is the top left corner of the rectangle, and the bottom right corner of the rectangle, the color, the thickness, and the line type. Line type is not something we are interested in. We'll go until the path of thickness. So yes, so we have CV2 rectangle, and you are going to be drawing it on the main colorful image, which is the IMG image, instead of the grayscale image. Now you are also going to specify the point 1, which is given by X and Y, and you're also going to specify the point 2, which is given by X plus W, Y plus each. So you're just going and pointing it out to the bottom right corner of the rectangle. So once you have specified the points, you also need to specify the color, and we'll say, okay, let's use green color. We'll say 0, 255 for green, and 0 for red. Everything else is green, it's 0, except the green color, which is 255. We will also give it a thickness of size 3, pixel level 3, and it should now draw the rectangle on the face for us. So let's run this. Oops, we are still displaying the grayscale image. Instead of the grayscale image, now we can display the IMG image, which should hopefully have the face detection for us. You can see that it's automatically detecting the face of the person, and it's also drawing the green colored rectangle that we wanted in this chapter. So it's a very simple code. You can see it's hardly a few lines. The only thing you're doing is you're doing some cascade classifier. You're initializing the cascade classifier. You're reading an image. You're converting it into a grayscale image. Then you're using the cascade classifier to detect the faces that are available. Normally, if you have multiple faces, it will go through all the faces in the face section and then draw the rectangle on all the faces. But in this case, in this particular image, the person.jpg image that we used, it has only one person in it, and that's the reason you don't need to go through all the faces. But if you had more faces, this function will just loop through all the faces, draw all the rectangles, and then display the output for us. So that's where the face cascade classifier comes in. I also have another image called group.jpg. I'll quickly run this for you. So let me change this. Group. In fact, let me copy this and oops, let me copy this so I don't mess up your original code in case you're going to be running this. And here I'm going to change it to group.jpg. The group.jpg is now a different image which has a couple of people in it instead of just one person. But let's see how this function operates. This one is going to take a little bit more time just because it has too many faces in it. And you will see that what's the kind of output you're going to get here. I'm going to skip this a little bit. So now we can see that the image has come up here. You can see the amount of images, the amount of people are present here, and the face detection that is running through it. Let me maximize this a little bit so you can see the intricacy of the face detection. This is a very noisy image. It has so many information. There's so much of information here, but it's still able to detect the faces in this image. And this cascade classifier is very lightweight. It used to be run in the old camera phones, the camcorders, the old camera phones, which did not have any much computing power, unlike the phones that you use now. So this cascade classifier was capable of running face detection in those small, low-end profiles. You can see the accuracy, the level of accuracy that's able to detect. Yes, there are some misses, there are some people who are not being detected, and some errors and mistakes here, but to the most part, it is able to give out the right information. Hello everyone, welcome to lesson number 3 of intermediate OpenCV tutorial series. And here, the first thing we're going to do is clone this repository by running this command over here. It will clone the repository, all the images that we need for this project. So once everything is done, go back and open this table of contents and go under the lesson number 3, shape detection. That is what we are going to work on today. So let's start the project by first importing all the libraries that we need. We need OpenCV, we need NumPy, which will import as NumPy NP, and we also need the Colab version for cv2_imshow. We'll use Google Colab.patches import cv2_imshow. So this function imshow is just for displaying the images for us. Let me increase this a little bit so it's easy for you to see. We will also make it full screen so we can clearly see what's going on. So we have the shape detection and we are just specifying all these libraries right here. The first thing is let's read the image. And the image is inside this folder, OpenCV, images, and shapes.png. So this is the image that we are interested in today. And we'll do that by reading this image for us. So we'll say, OpenCV, please read an image and save it under this variable called img. And you want to use OpenCV's imread function. And this function just needs the name of the file name and the file path wherever it is located. So it's located inside the images folder in the directory. and we call it as shapes.png. So this will just read the image for us. We can always test the image whether or not it read the right image by using the cv2im show function, and we just run this and we see there is an error right here. So it looks like we missed something. Google Colab patches from, so we need to import from Google Colab patches import cv2_im show. No worries, we fixed it. Now we can just simply rerun this and we can see that it's able to read the image and it's displaying it here for us. So good. Now, the first thing you want to do, since we are doing shape detection, we want to discuss and identify what kind of shape it is. So we know, I mean, from a human eye that this one is a circle, this is a hexagon, this one right here is a square, this is right here a triangle. So we, from a human perspective, we know what these images are. But if you were going to give this control to a computer program, how would the computer read through all these colors and identify these images? So of course we need some sort of algorithms in order to do this, and we'll see how we can do that. So we'll try to read these shapes and images through OpenCV or image processing perspective. So the first thing you want to do is convert this into a grayscale image, and we'll use OpenCV function convert color. So convert color, CVT color. This is just going to convert the color from whatever color we want to whatever color profile we want. So you need to specify the image that you want to convert this to. So IMG is the original image. And we also need to specify what kind of conversion we are doing. So we are going to convert from color to grayscale. So we're going to use CVT color BGR to gray. You have BGR to gray, and this color profile is just going to convert the colorful image into a grayscale image. We can always use the cv2im show function to see what kind of an output we get, and you can see that it's already converted all the colors into a grayscale profile. It does have the shape and the boundaries of the image, but it's all grayscale. Okay, so we have the grayscale image now. Now, the next thing we want to do is understand some of these functions, some of these images, some of these values in a more clearer way. And for that purpose, we'll use OpenCV's thresholding function. This thresholding function is responsible for converting anything that you are interested in, anything that your profile is interested in, into white, and then the rest into black in color. So this is basically a filter, and you can say, hey, okay, OpenCV, anything which is light, like this hexagon, this circle, the square, the triangle, these are all lighter colors compared to the background, which is black. So anything which is light, please make that into white in color. And everything else, black. So I'm not interested in them. I'm only interested in the white in color profile. For that purpose, we use OpenCV's thresholding function, and we'll call, hey, threshold, use this OpenCV function called threshold. This threshold function is a built-in function from OpenCV, which can take the source and threshold value and the filters and then convert that into a black and white image. So it basically filters the image to the values that you are interested in. So you specify the image, which is our grayscale image. Now you want to specify the threshold values. So we'll say, okay, anything which is between 50 to 255. Because we know white color is 255, so anything which is 255, and 50 is the lower end, and we'll see 50 should be okay in our case. And we're also specifying the type, which is not too much of an issue. We just specify 1 and we take care of this. Now let's see if we can display this image here for us. So cv2im show thresh. So let's see how this kind of an image looks like. And you can see that it's already converted everything into black and white. And yes, it's everything that we are interested in. It's all converted into one color, and the background is in another different color. So this thresholding function has already used a filter, and everything that we are interested in, it has specified them into one color and the background into another color. So that's the purpose of thresholding. So it's converting that into two different values, and now we can use that to our advantage. So now we have all the functions that we are interested in. We have all the images that we are interested in. Now let's start reading these different values from an OpenCV perspective. So OpenCV has a good function called as find contours. So this find contours function is a type of function that's able to go through all these images and go through this right here. You can see the circle, and it'll find all the contour, the outer contour, which differentiates these two colors. The black color and the white color, these are differentiated by this circle right here, and it will find that contour which is differentiating these two colors. So these two color pixel values that are being changed or being differentiated, it will identify the border of these pixels. So we'll use this function called contours, and these are just the H, and this thing is nothing but just specifying the history and the flag values. So we're not interested in that. We're just interested in the contours and the threshold. So CV2 find contours, and contours is given by contours. So you're just specifying the different types of contours that we are looking into, and we are specifying, okay, the contour should be taken out from the threshold image, and you're also going to specify what kind of contours you're interested in. And this is of course a binary image, since we use the threshold function, and we are now you're going to use different types of filter and pixel values. So you're saying, okay, it's going to be between 1 and 2, and right now you don't need to understand, you know, these two values. It's as long as you're putting 1 and 2, it'll work fine. You don't need to worry about why and not. So let's go into understanding what these contours are. So these contours are just specifying all these outer boundary of the pixel value of the shapes. When we have the contours detected, these contours are specifying information about the circle, this hexagon, the square, and the triangle. So it has information, it has the contours for all these shapes that we see here. And we will just loop through all these contours and go through the contours that we are interested in. So we'll say, okay, for cons, which are contours, or the contours, or for a counter, or inside these contours, for a counter, which is, so we're just looping through all the contours one by one by using the for loop, and you want to identify what are the points that are specifying the contours. So these are the points. In case of a circle, there are too many points since it's a circular image. But in case of a hexagon, you can see that there are 6 points that you need in order to define a hexagon. So these we'll use a function called as approximate poly DP, which is able to identify the number of coordinates or the number of points that you need in order to define your contour. So whatever shape you're working with, whatever it could be, how many points do you need in order to identify or in order to draw your shape? So we have this function called as approximate poly DP, which can give us an approximation of how many points we need in order to define our image or shape. So we have this function's name is approx poly DP, and this DP is defined. The DP is actually the name of the person who invented this algorithm, and his first name starts with a D and his last name starts with a P. I believe it's Daniel Pickard, if I'm not mistaken. I'll put it in the I'll put some text here to identify what's the right name of the person. But this approximate poly is able to give out the minimum on the number of points that you need in order to identify your contour. So this approximate poly just needs the information about the contour that we are working with, and it also needs some sort of an epsilon value. This epsilon value is nothing but the error or the amount of error. Oh, you know what? They have the name here. It's Douglas Pecker. So Douglas Pecker is the name of the person who invented this algorithm, and that's why it's called approx poly DP. So this function takes this information called as an epsilon. This epsilon is nothing but the approximation value, or you could take it as an amount of error that you're okay with when you're identifying this function. So it's one of the best ways of identifying, or one of the best ways to denote the function or the epsilon value is by using the arc length. And the arc length, if you multiply it by 0.01, whatever value you get, it'll be more or less acceptable for our error purposes. So as for now, just understand we're just converting this. We're just specifying the amount of error that we are okay with. And we say, okay, arc length, and we tell the contour name and true. So let me go this on this side so you can see what's happening. So we specified the contour. We are specifying the epsilon value, which is given by this, and we're just giving by the arc length of that contour. And based on that, now we need to just specify, okay, we are just going to be whether it's a closed curve or an open curve. In our case, all the curves are closed, so we'll just say true for closed. So we are now specifying all the approximate value, and this approximate will be able to read all these contour values and give us the value of the each and every shape. So let's print this. So we'll see what is happening here. So we'll run this, and you can see that it's able to go through all of these, and it's giving us the points for each and every contour. So now let's see. Okay, we have the approximate, which is giving us the coordinates of the shape of the points. And and these are, you can see it's form of an array. It's an array which is going through all of these points and giving us. So if we go through the length of the array, instead of printing the whole array, if we just print the length of an array, you can see that's giving 4, 6, 3, 16, 4. And I wonder what that is. So let's go back and print this image or read this image for us. cv2 underscore im show and threshold, and just rerun this again. So you can see that this is a shape, and it's giving us 4 points, which probably represents a square, and it's giving us 6 points, which is probably representing the hexagon here, then 3 points for the triangle, and 16 points for the circle, because circle is, you need too many points in order to define a circle. And the last is again 4 points, and these 4 points is nothing but the outer image, the bigger boundary of the image, which it's not visible here since the background of the code and this thing is all in white in color, but that's the outer boundary, so it's given by 4 here. So good. Now you are able to differentiate, and you're able to identify, okay, approximate is able to give us the length of the coordinates. Not only the length of the coordinates, also specify the coordinates or the points that can define your shape. So you have approximation, and now you're going to say, okay, if the length of approximation, so or we can say, okay, number of points n is equal to length of approximate. So if n is equal to 4, then this is a square. So you are reading a square. So once you have the square written, you can draw the contour across the square. And you have this function called as cv2 draw contours. And this contours function can draw a contour of whatever size or whatever shape you want based on the values that you are interested in. So draw contours using the on the image called img, and since we had this image right here, the original image img, we will draw the contour on this image. We'll say img, please draw the contour using the contours that we have inside the cnt function, inside the cnt variable. And once we have this, specify where or whatever the size or shape of the contour is. So we'll say 0, the contour index, and the color, which is 255 for our case, and then the thickness, where we're just specifying what kind of contour image or what kind of a thickness it is. So we'll say, okay, for now, we're only detecting the square and drawing the contour across the square and then displaying the image for us. So we'll say cv2 underscore im show img. Okay, we don't need the IMShow threshold function. We're just interested in the IMG function, and let's run this. So you can see that it's now fully black in color, and the reason for that purpose is we are not able to read the image. We have already converted that into an image here for us, and we are also drawing the image with the -1, and this -1 has basically drawn it's filled the whole image with the color that we were interested in. And the image, the square, was the big rectangle, the big boundary box of the image, and for that purpose it has colored everything into that a black color or blue color value. Now if we were to say, instead of -1, let's say 5, let's see what kind of an output we get. You can see there's a boundary right here which is almost blue in color, and it's specifying that it's a thickness of about 5. If I were to put 50 maybe, let's run this, you can see there's a bigger boundary which is much more visible, and there's also a boundary right across this square box here, and you can see that it has a boundary of about blue color right across the square which is green in color, and also across the big square of the image. Now you have the square. If we were to say, okay, instead of the square, I'm interested in the boundary of the hexagon. Let's run this, and you can see that it's drawn a boundary across the hexagon. So we are using the approximate function. Using the length of the approximate, you can identify whether it's a hexagon or a square or whatever it is. Since we put n is equal to 6, we'll say it's a hexagon, and we'll reduce the thickness of this, say, to maybe 10, and we'll rerun this, and it's able to draw a contour across the hexagon. And it can also write down that, yes, print, this is a hexagon. So this function can now tell us that this is a hexagon. Now once we have this, we'll say we have a hexagon here. So we have a hexagon here. Now it's able to tell us that this is a hexagon. Okay, good. Now let's go through all of these. So if elif n is equal to, we had the triangle which is given by 3 variables, we'll say, okay, this is a triangle, and we can print triangle. Okay, we found a triangle, and we can also draw the triangle by using the contours function, and on the same image with the contour value that we found. And here in this case we will use a different color. We'll say, okay, maybe you can specify the contour index, and we will use a different color. So 0, 255, 20. So it'll be a green color contour for a triangle. And is our triangle blue in color? Yes. So we can use a green color rectangle triangle, and we'll give a thickness of about maybe 3 size. And let's run this and see if we can see a green color boundary across the triangle. So yes, there is a boundary of green color right across the triangle, which is very good. Now once you have the image, now you're specifying, okay, so elif, if n is anything greater than or n is equal to or 9, so that's basically your circle. So this is a circle, and print, we found a circle. cv2 dot draw contours, circle on the img image function using the contours that we are interested in, and then you're just specifying the index. We'll put it as 0. No worries on that. And then the color profile, so in this case we will maybe use 255. I think this is a pink color. Let's see what kind of an output we get, and let's run this. You can see, oh, it's giving us a yellow color circle boundary right across the circle. So you have everything, just the square is left. So square, we'll say, okay, LF n is equal to 4, which is given by its square. This is a square. We'll say print b on the square. Okay, good. We are also going to draw the function contours img cnt and you're specifying the index. Now you're also specifying the color we want. We'll say 255 comma 255 comma 0 and a thickness of 3 size. Let's run this, and it's giving us some sort of an error because we missed the bracket here. Instead we put it here, so it should be fine now. And yes, you can see there is a boundary right here and there is a boundary over here as well. So you are specifying, you're able to differentiate all these colors, and it's able to differentiate and see what kind of a shape it is, and you can identify what kind of shapes that we are working with in this particular image. So if we do a quick recap on this, we did quite a bit of things in this lesson. We looked into the thresholding value, so where we can threshold, we can filter the image of a grayscale image into whatever color profiles that you are interested in. And you can also use the find contours function, which can go through the image and find all the different types of contours that are representing the shapes in the image. And then using the approximate poly DP, you're able to identify the points, the approximate points that you need in order to draw your contour once again. And once you have the contours, then you go through all of the length of the approximation, and based on the length of the approximation, you're identifying what kind of a contour is it. If it's a if it's a 6 coordinate contour, it's a hexagon. If it's a 3 coordinate contour, then it's a triangle. Similarly, you can identify if it's a circle or a square. So this is basically helping us to identify the different types of shapes from an OpenCV, from an image processing perspective. Hello everyone, welcome to this part 3 of the OpenCV tutorial series. Here we are going to try and attempt to do a project. And this is about tracking a ball. You can see this video in front of you. The ball is moving around, and the idea is to track the movement of the ball at any point. So from a human perspective, we know where the ball is moving. It's moving right, left, right, in random fashion. But how would you do that from a computer vision perspective? How would you make a computer understand where the ball is moving? So let's get into that. So the first thing we want to do is, of course, import OpenCV. Let me make this a little bit big, maximize this everything, so it's very easy for you to read. Okay, we have import CV2, import numpy as np, and from Google Colab patches, import CV2 underscore imshow. Before we do all this, let's go ahead and clone the repository. And if you go into the table of contents and OpenCV page 6, the first step just above the part 1 is where the GitHub repository is, and we do want to clone this repository. This will allow us to access some of the project files that we are going to be using in this particular project. So you have the OpenCV tutorial folder, and inside this, you will see this videos folder. And in this videos folder, there's a video file called video.mp4. And this is what the file or the ball tracking file is that we'll be using. Okay, let's come back to the table of contents. Let's go into a project, which is the tracking a ball. Let's continue our coding. So right now we have just imported the libraries that we need. The next thing is, let's open the video file that we just saw. So we can call, OpenCV has this function called video capture, which is basically able to read a video file for us. So we'll create a capture variable called cap equal to CV2 video capture. And this video capture is able to read a video file or even a webcam for that matter. If you wanted to read a webcam, of course, you can't do this on a Colab. You can do this on your own desktop computer. And if you just put down 0, it will start reading the default webcam that's connected to your computer. But instead of that, let's read a video file that we have here in this Colab. So we have it under the folder called videos/video.mp4. So coming back again, just to make sure, we are under the OpenCV tutorial folder, and inside that there is this videos folder /video.mp4. That's the file that we are going to read through our capture variable. And this capture variable is capable of reading through every frame of the video file for us. And the way we do that is by reading, hey, capture, give me a frame from your video file. And cap has this function called read. This read function is able to read through the video files and then give out the frame that we want. But now a video file consists of multiple frames. It has millions of frames, hundreds, thousands, many frames that are stacked on top of each other. Then when they play in a sequential format, it looks like a video. So if we just read it once, it'll just give you the first frame. If you read again, frame equal to cap.read, it will read the second frame. Similarly, if you read it again, it'll read the third frame. So you have to keep going and throwing and reading through all the video frames. That's a very cumbersome format, and you really don't know how many frames there are. So instead of reading them individually, we will read them through a while loop. And we will open up a while loop. We will say, hey, while loop, please start reading the video file for us. But you want to read the video files only and until the videos start or spitting the frame files. So it should read only until the videos have enough frames to read. And once the video comes to the end of its file, you should stop reading. Otherwise, you'll be running in an infinite loop. So we'll say while cap is open. And this flag is capable of reading whether or not there is something reading through the video file or not. And then now we will read the frame. We'll say frame equal to cap.read. So it will read through all the frames of this particular read function. It will go through all the frames that are available in the video file and then give it in our frame folder. Now, OpenCV also allows us to do some debugging. It allows us to make sure what we read is good or not. So it has a flag, and we'll call this the red flag. And this flag is capable of letting us know whether or not there was a frame read or not. So if there was a good frame and if a real frame came out of this video file, then this red will be equal to true. Otherwise, it will be false, stating that no, there was no frame read. So you don't need to take care of anything. The frame is nothing. So this red flag helps us also keep a checkpoint stating that, hey, is there a frame or not? And if there is a frame, continue with the next process of the project. But if there is no frame, then don't bother. So we'll keep an if statement. We'll say if red is false, don't bother. Don't bother the while loop. Don't bother continuing with the project. Just break out of it. And this is a condition that we will create just reading the red flag. This flag is able to, it's whether or not there was a success or not, whether a frame is read or not. That's all we're doing here. And this frame is now going to be read through all the frames of the video file, and subsequently, sequentially, it will have all the frames one by one. Now let's see what we should be doing with this frame file. This frame file, we are interested in identifying the color of the object, and we are also interested in identifying where the object is in the video. So we did in the previous projects, in the previous lessons, we looked into color detection. In this color detection, we saw how we could detect particular colors, like you had the yellow color, the green color, the red color. Now we know our ball in this particular video is of yellow color. So we can maybe use this particular code, we can create a mask, we can do some bitwise and find the position or where the yellow color is located. That's a cool thing to look into. Now, coming back, we'll use that same system for our current project, and we will do some yellow color detection. And for that purpose, what do we need to do? First thing we want to do is convert the color into a HSV image. Again, the reason I'm going through this is because we have already covered this in the previous lessons. And if you need, you can always go back to the color detection, color changing profiles, and you will understand what we are doing here. So we are now converting it into a HSV image, and we use CV2 color BGR2 HSV. We bring it here. So you can see that it's now converted into a HSV image from a RGB or a BGR image in OpenCV format to HSV image. This HSV is now able to help us detect the yellow color specifically. And we saw there was a lower bound and upper bound of hue, and we will use that here. So let's go back to this code, and you have the color detection. And it's easy to copy and paste the colors that we saw here. We have the lower hue and the upper hue, and we'll copy this. I'll press the Control-C button, and coming back to where we were, the table of contents, we want to go into the project folder, and here we will paste what we need here. This needs to be a little bit indented. So here lower hue is representing the lower bound of the yellow color, and the upper hue is representing the upper bound of the yellow color. The next step we want to do is create the mask, and the mask would be given by using the CV2 in-range function. So in-range is going to look into the image, and wherever the hue value lies between these two ranges, and the hue, saturation, and variance values lies between this range, it will give out all those pixels in a different color. So it will highlight those pixels for us particularly. So we'll say, okay, CV2 in-range function, do your in-range magic on my HSV image using the lower hue and the upper hue range that I have created for you. So good job. You have created the mask. You have now identified the yellow color specifically in the video. Good. Now, what is the next step? The next step is to identify where this yellow color is residing. And for that purpose, we used a function called find contours. And we did find contours just in the previous function. If we go right here, in the previous function where we did draw contours, find contours. So this is the previous lesson that we covered, where we were doing shape detection, when we were using find contours to identify the different shapes that are available, different colors, and then also draw those contours. And we will use some of these functions in our project as well. So coming back to the table of contents, project, coming back to this place. So we have the mask, and we have now going to create all our contours. So the contours function, we will create, okay, contours, and whatever x the contours function is able to give us, we are not interested. We are only interested in the contours that the find contours function is going to help us find. So there is a function called CV2 find contours. This contours function is now going to help us in identifying the different contours that are available in the image. And this function needs the mask that we just created. It also needs some sort of functions that are going to specify what kind of a contour detection it's going to do. So in this case, we are going to be using the pre function, and we call it as the CVT RETR tree. This is just understanding these are different types of contour detections, and we're just using a specific type for our project. It doesn't matter. It's a simple contour detection that we're doing here, and it's not going to affect what type of contour detection you use. And this the approximate simple. So these are different types of filters that are used, a different algorithm altogether, and we will be just using that to detect our contours. Once we have the contours detected, well, good. The next thing we want to do is then try to identify where these contours are. So we'll say, okay, for now, I don't know where the contour is. So I'll say that contour has a center point, which I don't know. And for now, I'll put it as just none. Now, if my frame has contours, so if my length of contours is greater than 0, which means that I have contours in this, otherwise it'll be 0. So if my contours is greater than 0, yes, let's go about and identify where my contours are located. And for that purpose, we will first identify which is the maximum, the biggest contour in my image. And for that purpose, we'll say, hey, C, which is the maximum contour, use the max function of Python to detect which is the biggest contour of all the contours. And you can use the key function. And how do you identify which contour is the biggest? You are going to use the CV contour area function. The CV2 contour area is able to give you out the different types of contours and their areas, and it will give out the maximum size of the contour. And you can store that under this variable called C. Once you know which is the biggest contour, good. Now let's find out where this contour is located. So initially we detected that it's center of none, but now let's try to identify where exactly, what is your coordinate. So now we can use a tuple called x comma y, which is going to be the center coordinate and the radius. And OpenCV has this function called minimum enclosing circle. And this minimum enclosing circle can take a contour, whatever contour you give. And in our case, we're going to give this contour called C. And it's going to take that contour and identify what would be that circle, what would be that minimum circle that can enclose the whole contour. And what the circle is defined by the center point and the radius. That is the circle which will be enclosing this contour that we have here. So now you know where the center is, you know where the radius is. So very good. Now we also want to identify where exactly the moment file is. So we have the moments which can be given as m equal to cv2 moments. So this is another way where you can identify the center of the contour by using moments. Moments is nothing but specifying where the center of the mass is, where the centroid or where the main center of the contour is located. And for that purpose, we'll use a try function because it's prone to errors. And we will say, hey, try to find the center. And I'll say center is equal to, there is this formula. And it's going to sound a little bit confusing here, but stick with me. What you're just basically identifying is the moments of different types of contours, of different location of the different coordinates of the contour. And based on that, it can identify where the center or where the centroid of that contour is located. And that formula is given by int moment. And this is an array, which is given by 1, 0, which is nothing but the corner, one corner. And then you are also dividing this by another moment, which is given by m00. So these are two moments which we are just defining, and that's the x coordinate. Similarly, the y coordinate is given by int moment and specifying which moment is this, the next coordinate. And then you're also dividing this by the base, which is given by m, and you have m, 0, 0. You're just defining where the center of the coordinate is. So once you have the center, now you can also identify where to draw these centers. So we can draw the center, CV2, circle, good. And your frame, you're going to draw on the frame, the original frame that we had. And we're going to draw using the center of the image. Good. So we have the center, and we're going to say, okay, the radius of this circle is going to be, say, 10. And we are going to give a color of maybe blue color, 255, 0, 0. And we're going to fill this, or the thickness. Thickness is going to be -1, which is nothing but specifying that the whole circle should be filled with this color. Okay, good. So now we have drawn the circle. Now this circle, this center is specifying one location, one point of the ball. Now we are interested in identifying all the different types of contours that can be available. So you want to store the center of this ball at every instance. So for that purpose, let's define an array. An open array will say ball is equal to an open array. Right now, we don't know what this ball is going to have, but this ball is supposed to have all the coordinates of the center of the ball at any instant of the video. So this ball array is going to host or have the center coordinates of the ball wherever or whenever it is moving in the video. So we'll say ball dot append. Append is just adding to the array. Append the center, which is the coordinate of that ball. So you just right now storing the location of the center into the ball array. So good. And if there is an exception, we'll go ahead and pass. We're not going to bother about it. Now we have the center of the coordinate. We drew the circle at that instance, and we are also appending the center, which is very good. Now let's use this ball array to draw the track or the movement of the ball. So for that purpose, we'll say if the length of ball is greater than 2, because the reason I'm saying greater than 2 is because you want to draw a track. A track is nothing but a line, and the line can be defined only by 2 points, a minimum of 2 points. So in order to draw a line, you need to have at least 2 points. And for that purpose, I'm asking, hey, ball, are you length of 2 or greater? If you're 2 or greater, let's go ahead and draw. So I'm just going to draw this now. For I in range of I, in range 1 to length of ball. So I'm just going to loop through all the elements, all the center coordinates of the ball, right from 0 to the length of the ball. And we're going to say, oops, let me put the colon here, and we'll say draw the line or the track that I'm interested in on the frame using ball's initial coordinate, which is the -1, which will be the 0th or the index 0, and the next point, which is the ball I. So between these two coordinates, between these two center points, go ahead and draw the line that I need. And give me a color of red. We'll say 0, 0, 255, and a thickness of, say, 5. Okay, so now you're able to draw a line. Perfect. Now this is where we are able to show that, yes, our OpenCV project is able to draw, not just detect where the circle is, but at the same time also draw the line showing where the ball has moved. So very good. Now, how do we take this information? How do we show it to the end user that we were able to do this? Since it's a video file, if you start displaying it here on Colab, it'll be a big mess. Instead of that, we will read this video file, but we'll also save it as a video file. And OpenCV allows us to create videos. So using a video writer function. So we'll call a variable like we call the variable capture to read videos. We'll call a variable called output or out, and we'll say OpenCV, use your video writer function to write a video file for me. And for that purpose, you're going to create an output AVI file. And this output AVI file is going to have the type of the video that we are interested in. You're going to store all the new frames that you just created into that. So we'll say, okay, very good. I'm going to create this output.avi file, but what kind of a video file do you need? There are different types of video files. There's different types of compression of video files, I should say. So there is the MJPG, which is nothing but moving JPEG, moving JPG images. So we'll use that, and there are different other types of compressions, and we will use MJPG, which is moving JPEG. We'll say CV2 video writer, and this 4cc. Oops, 4cc. And this 4cc is nothing but the video codec that we are interested in. And in our case, we'll say MJPG. Oops, capital G. So we have MJPG, which is the type of video codec that we are interested in. We are also going to specify the number of frames per second. In our case, it will be 10. And we also need to specify the size of the video. And the original video that I had created, the video.mp4 that we used, that was at a resolution of 1920 by 1080. So we'll create the same video file, same size. You can use whatever size you want. But just so, because I'm doing a screen recording, if I do something lower, it might come out very bad on the screen. So I'm saving it as a 1920 by 1080. Now this output file, oops, it's jumping out. Okay, so this output file is able to write whatever frame that you are interested in this output.avi folder or AVI file, video file. So we have this output function, like we use the capture function, and we use capture.read to read through all the frames. Similarly, this output function is capable of writing the frames. So we can say out.write frame, and this out.write will just simply write the frame that we newly created here into the output.avi file. And it will loop through all the frames until this while loop is finished, until the red flag says no more frames available. You went through all the frames, so you're done. And until it does that, it will go through and write all the output frames for us. And once everything is done, it will go ahead and you can release the output file. I think this should be indented a little bit on the left side because we're doing it in the if length contour side. So we want to do this once it's out of the if statement. At the final end of the while loop, once you have done all the manipulations that you want to do on the frame, and then just simply write the file onto the output.avi. So good. Now let's go ahead and run this. Let's see if we come across any errors. And it's taking a few seconds. It's running through all the frames for us. Okay, so it seems to have run, and we can now open this file, and we can see under the videos, not under the videos, under the output main OpenCV tutorial folder, you have the output.avi, and I can simply click here and press download, and it will give you this output for us. Hello everyone, welcome to project number 2 of our OpenCV tutorial series. Here we are going to try to attempt face recognition. So for that purpose, the first thing you want to do is go into runtime, and this is the link which will already be there in the description for you. Just go ahead and click on change runtime, and you want to make sure you're under GPU and then just save, because for this purpose we would be using the GPU cloud on the Colab. And I'm going to maximize this a little bit. So in order for you to go into the project 2, if you go into the contents page and you have projects right here on the part 3 section, and we are under face recognition part. So once we are in this section, we want to run this particular code. Here we are basically cloning the repository, the face recognition repository, and we have some images and some files that we are going to be using for this particular project. We are also going to be installing the face recognition API, and this was, I believe, designed by Adam Gateke. That's the name of the person. If you just Google face recognition, just go into Google and we'll do Adam face recognition. So this is considered to be one of the easiest, one of the fastest, and one of the most accurate face recognition libraries out there. And it was developed by this gentleman, and we are going to be using it in our project right now. So coming down here, once we run this thing, it will go ahead and clone the repository. It will also install the face recognition library for us. And we are also asking Colab to change the directory to face recognition so that we can access the files directly. So it'll take a few seconds, and here in this section, now you can see there is a face recognition folder. And right here in this section, you can see all these files are now available for us to test. So this project is basically divided into 3 steps. One is cloning the repository, installing all the dependencies that you need for this project. The second is encoding, finding the encoding profile of the face images. The third is using those encoding profiles to now detect unknown faces. So we'll go into the basics of each of them and try to understand what it is. So basically, a face has its own properties. A human face, the way a person looks, is defined by their eyes, the shape of the eyes, the distance between the eyes, the nose, the size of the lips, the placement of the ears compared to the rest of the face. So these are all features that define a person's face. And encoding is just using those features in order to create a profile for a person. And those encoding details are specific to that person. So it's not going to be common. It's not something which can be replaced with another person's encoding. A person's encoding profile is his or her own encoding profile. And we are going to be using that for our project today. So the first thing you want to do is import face recognition library that we installed up there. We are also going to be using NumPy today, NumPy as NP. And before we go into further details, let me maximize this a little bit. Also move this guy up so it's much more readable for us. A little bit more, I think. Okay, perfect. So import NumPy as NP. We are also going to be using Google Colab's CV2_IM_show so that we can display the images here in the Colab. And for that purpose, we will be using Google Colab patches. And from there, import CV2_IM_show. We might also use, of course, OpenCV. So don't forget about OpenCV. That's the bread and butter of this project. So once we have OpenCV and all these libraries imported for us, we will now go ahead and create the encoding profiles for each face images. So if you go into the project folder under the face recognition, you can see there are some images like the Donald Trump image, Elon Musk image, Earthrow, Jeff Bezos, and these are all images of people who we already know. And these other set of images right here, unknown, 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 these are all images that the computer or the program does not know, and we will be using these images to use for face recognition in the next step. So for now, we will use Donald Trump's image and Elon Musk image and Jeff Bezos image to create the encoding profile. So the first step is creating the encoding profiles. And for that purpose, let's create the encoding profile for face 1, face number 1, and let's call this maybe Elon Musk's face number 1. And we will call the face recognition library up there. Hey, face recognition library, please come to our help, and we want you to load this image file of Elon Musk. I have Elon Musk in my project folder, and it's called Elon. Let me come back here. It's called elon.jpg, and you just use Elon JPEG to load the image file for us. And good job. Okay, so once face recognition has loaded the image file, now we will also request our face recognition library to create the encoding profile for us. So we'll say face 1, your encodings are given by face recognition. Please, face recognition library, come back again, and we need your help this time to create face encodings. And for that purpose, we will call face 1, use the encoding profile from face 1. And once we have face 1, you're going to call, okay, only use the array 0th element of the face 1. So that's now created the encoding profiles of face 1 encodings. Perfect. Similarly, let's create the face encoding profiles for the other gentleman. And for that purpose, we'll just copy the code from here and paste it here, do another paste here. Now this one we will call phase 2. Okay, phase 3, we will change this to phase 2, we will change this to phase 3. And instead of Elon, we might say Donald Trump. And that's the file name, Donald Trump. The next is Jeff Bezos, given by this spelling. So come back here, and instead of this, we'll call Jeff Bezos.jpg. So it has now created the encoding profiles for all the 3 images. Let's bring them in an array so that the program can later call them individually. So we'll say, I will create an array called known face encodings. So these are the encodings that the program already knows, and we will call them inside an array. Okay, so under this profile, we'll call face 1 encoding, comma face 2 encoding, comma face 3 encoding. Good. So this is my known face encodings. Now I will also give these encodings names in the same order. So we'll say known face names, and these are the names of our people who we are training them. Oops. Okay, come down here. So we'll say the first guy is Elon Musk. The second person is Donald Trump. And the third person is Jeff Bezos. Okay, so we have all the 3 images. So we have created the encoding profiles, and now we have all the image names also inside an array. So whenever this encoding 1 is called, it will refer to Elon Musk. Whenever encoding 2 is called, it will refer to Donald Trump. Similarly for Jeff Bezos. So in this section, we only created the encoding profiles. Now coming down to the next section. This is creating the run face recognition. So we are now going to use those encoding profiles to create and start running the face recognition aspect. So let's use one of the unknown images that we have. And we will probably use unknown EL, and EL is basically the abbreviation for Elon Musk, DO is Donald Trump, ER is Earth Roll from here, and JE is Jeff Bezos. I don't know why I left it as JE, and you might also notice a spelling mistake here. Just be mindful of this particular image. It's already an error, so I'll try to remove it in the repository later on, but for now, for the purpose of this video, we'll roll with it. Now, the first file name we will call, okay, let's read the first file, and we'll call the Elon Musk's image, which is the one here, unknown el.jpg, and we'll call unknown el come down. We're going to test you and to see who you are and whose name you carry. So you have file name, and we'll say this unknown image is right here for us. Oh, it looks like Colab doesn't like us to use GPU runtime. It's giving us an error, but don't worry, because very soon we are going to be using your GPU Colab, and at that point they won't be so angry with us. But let's come down. So we are now reading this unknown image of Elon Musk, and we will use face recognition dot load image, the same thing that we did here. In fact, we might copy this whole section from here, and we will just load this image that we grow, this function we have here. So we'll say load image file, and we'll use the file name that we created up here. Perfect. Now we have unknown image to draw. We're going to call this image as something that we are going to be using to write down. In fact, we don't need to draw this image. Let's call the encoding profile for this guy. So we'll say, okay, where are your face locations and where are your face encodings? So you have your face locations, which are given by face recognition dot face locations using the unknown image that we have up here. Now we are also going to be creating the encodings, and we'll use the encoding function face encodings of this new image that we just uploaded is going to have face recognition's encoding and face recognition face encoding unknown image and face locations. Okay, so we have now created the encodings for this unknown image. Very good. So let's now try to compare this face encodings with the encodings that we already have here. For that purpose, we will now use a for loop. For, and we'll first zip the face locations and the face encodings. So we'll do zip face locations and face encodings. The reason for that is because we want to compare both of them together. So we have face encodings as well. And these face locations and face encodings can be compared in two different formats also. So we'll say face locations will give us the top, the right. So these are the top, right, bottom, and left corners of the face. So you have bottom and left. So this is referring to the face locations, which we will get it from this zip file. And we also have the face encoding for individual. You have the face encoding and the face locations. Face encoding is for the individual faces, and this is just the array called face encoding. So you're reading through each one of them, looping through the for loop. Once you have that, now we will try to create a match, and we try to compare our face encoding from here to the face encoding that we already know from here. So let's go ahead, do that for us. We'll say matches, and matches is equal to the comparison between the face encoding of this new image versus the face encoding of the images that we know already. So come here, face recognition dot compare, and this is face recognition's function. So it's going to compare the faces from our known face encodings and the face encoding that we have here. Perfect. Now, initially, we will call our face, the unknown face, as unknown. Unknown. I don't know you. Initially, we will call it as unknown because later on, once the program is able to identify or recognize whose face it is, it should automatically replace this name with one of the names that we have here. Okay, coming back. Now, we are trying to compare the distances from the comparison that we created here. We'll say face distances is equal to face recognition dot face distance known face encoding comma face encoding. Now here we're just creating again that distance, and then now we'll try using this distance. We will try to now identify which one is the best for ourselves. Coming down here, we'll say the best match index. Now this is the index of these three images. So this is 0, 1, 2. So you're just identifying which index it is. We will say it is given by the numpy of minimum distance between the face distances. So all the face distances, this is nothing but it's identifying all the face distances, and now it will give us the least face distance. So we'll say, okay, the least face distance from the face distances array will be my best match index. Okay, perfect. Now, if matches best match index is available, give me the name of our known face names. So we'll call this known face names, and we'll say the best match index is your new name. So this is basically the face recognition aspect. So you're first identifying the face distances, and from the face distances you will come to know which is the minimum, which is the least distance between the original face and the unknown face. So that distance will be considered as we'll come to know our index, and we will use the matches that we use here to then call that particular face name. And we'll use our known face names array to get the name of the real person. Once we have the name of the person, now we can go ahead and draw the bounding box on the face and also put the text so we as the user can identify who this is. So we will use OpenCV's draw functions, which is the rectangle, and the put text function to put down the text in the bounding box on our image. So we'll say CV2 rectangle unknown, and you're drawing it on the unknown face here, the unknown image. In fact, let's read the unknown image that we have here. We're reading it through the file name. We will also read it through OpenCV. We'll say unknown image to draw, and this is the function that we will use. CV2 _im read file name. Here we are reading it in the OpenCV format, so OpenCV can use this image to draw our rectangle. We'll say OpenCV here, come here, put it down here. Once we have the OpenCV image, we can draw the rectangles, and the rectangles are defined by the bottom left or the top right corner. So we say left, top, right, bottom. Perfect. So now you're defining the color. We'll say green color, 0 to 55, 0, and a thickness of 3. So it will take care of the drawing of the rectangle for us. Similarly, we'll now write the text of the person that we know. We'll use the unknown image to draw here, and we'll write the name, whatever name that we want to put, by using this name string. We'll say name, And we will say, let's write it on the top left corner of the rectangle, which is given by left top, but we will give it a little bit of indent on the top. So we'll say -20. It's just above the top left corner of the image. And OpenCV has certain fonts that we can use. So we'll use the basic font, which is the font Hershey, Simplex 10. Color, we'll give it as maybe red color. And we will use the thickness of 2 and the line format of AA. CV2 line underscore AA. This will just simply write the text for us. Once everything is done, once the for loop is also completed, we will ask our Colab to please go ahead and display this unknown image to draw that we just created here. So once we have this thing, OpenCV should go ahead and run this. So we'll go ahead and run this. And it looks like there is an error here. The error says invalid syntax. And it is probably because we did not say where are we getting this from. So we should say face encoding top right bottom in zip. We have to say in zip, and that should take care of our error. Looks like there is still an error and they are not happy because we put down too many rectangles, at most 6 arguments, and it looks like we gave them 8 arguments. How come? So we have the unknown image. Oh, did we say rectangle? Instead of rectangle, we should have put text, because we are putting up a text here. And that should take care of our thing. So we can now see that it is able to detect the person, and it's also able to put the bounding box on it. And if you go ahead and open this folder and open the unknown EL folder here, you can see the original image is right here. And this is the face recognition image. So let's try some other image. We have a couple of other options. We'll open the unknown, which is basically Donald Trump's image, and we'll see if the file is able to detect it for us. So we'll say unknown DO here, so it can read this new image, and it's able to draw the bounding box on Donald Trump's face. So it's able to do the face recognition aspect, and you can see it's pretty fast. It's able to do it almost in real time. Now, this is something which is done in Colab. Now, if you want to do the same thing on a desktop or through a webcam, the same thing can be applied. Where we are reading a file name, instead of that, you will be supplying it through a webcam, and you can use a while loop, a true while loop, which would continuously loop through all the images of the webcam, and then pass this as a function. So this whole code right here can be made as a function. So we'll say, okay, def, and you can say some function, and you can pass the image that we want. And instead of this image, we'll say file name. So we can then replace this file name with here. So just uncomment this. Instead of taking it from here, we just call this as a function. We bring everything in this as part of this particular def function. So we'll say, okay, you're part of this def function. And once we have it here, we can now, instead of displaying it here on the browser for ourselves, we can then return this variable. And that will go back to the desktop where who is that while loop who is calling the images to return. I'll go back and undo our changes, because that is something which we cannot do here in Colab, but it's just an idea if in case you are interested.